So when we look at this equation, we could see that energy equals mc squared. C is the speed of light. Now, it's a constant in vacuums. This is speed of light in vacuum. And if you know the speed of light is 3 times 10 to the 8, I square it, I'll get 9 times 10 to the 16. That's that number right down there. Multiply that with the mass, and that's how much energy you get out in joules, mass in kilograms, of course. Whoa, that means that a little tiny bit of mass, I can make a whole amount of energy. And yep, that's basically what the nuclear bomb and the nuclear power plants are all about. But they're not as efficient as we think they are. Let's take a look and see some of those things. Let's just look and see how much mass would you need to produce 1 times 10 to the 18 joules. So that's a lot of energy. And if you do all of the math, turns out to be only 11.1 kg. So 11.1 kg can create a whole amount of energy, amount to power the US for quite a few months, maybe even a few years. All right, here's a nuclear power plant. It only converts about 1 kg of mass into energy in the entire year. Okay, so you could imagine we were just talking about 11 kg, 11 power plants. How much energy would they produce? And then we look at the sun. The sun is a totally awesome producer, changing in terms of converting mass to energy. And recall, when all of this stuff is happening, there's still a bunch of mass left over. So only a small portion of it is actually converted to energy. So here it takes a lot of nuclear fuel, but only 1 kg of mass actually is converted to energy in a whole year. And the sun here, every second converts 400 billion kilograms of hydrogen to helium. And in that, 4 million tons is converted into energy every second. I just kind of understand how much energy that is being released by the sun every second. And of course, it's being spread over a huge amount of area, and it's only a tiny amount of that falls upon the sun, on the earth, I'm sorry. So there we go, E equals mc squared. And you can kind of, if I give you the numbers, all you need is the speed of light, which is 3 times 10 to the 8. It's a constant. And so you should be able to figure out energy or mass. So, be able to make sure that you can do these calculations on your calculator and play around with them. Okay. We already know this. I'm not going to spend much time about it. You guys all know what the atom looks like and all its little parts. Here is nuclear fission going on, which is a process that happens in nuclear power plants. And so we see that a lot of elements are unstable. That means they are radioactive, and they spontaneously, their protons or neutrons decide they want to become something else. And we have a process that goes on. With these larger atoms, such as uranium and all of these other ones, plutonium, etc., they have a bunch of extra neutrons in some of their isotopes. So all of them also exist in many different isotopes. And so if the number of neutrons becomes really large in an atom, it becomes unstable, and those neutrons want to become into protons. What we also see is that if you have additional neutrons added into an atom, that means if I shoot neutrons into an atom, and I increase the number of neutrons in there, I make it unstable, and that atom splits up into a smaller atom and releases what's called sometimes an alpha particle, which is a helium nucleus, 2 protons and 2 neutrons together. And again, as these changes are taking place, some of the mass is being converted to energy. And it's only that is, utilized, and which is why only a small fraction of the nuclear fuel that's being used is actually being converted to energy. And then we have a lot of waste, which is again another problem we need to take care of. The two processes, nuclear fission, this is where atoms are split. I shoot neutrons into this atom, make it unstable. It splits into smaller atoms.